Every year we celebrate February 28 as a National Science Day to commemorate the invention by the genius Sir C.V. Raman. So I'm not going to take more time on this. My name is Nityanandan. I'm Assistant Professor in Physics Department. I have with me Anupam Gupta and Mayuk. So as you, I just want to tell you that this is event consists of three, and even within three events. There are three events in this. One is this National Science Day. We also have a Research Scholars Day, and we also today have the inauguration of our Astro facility. Right. So first of all, I would like to thank all of you for joining, and I invite our director, Professor V.S. Murthy, to first come and take the dais. Yeah. So yeah, followed by our chief guest and our head of the department. So thank you very much all. So we'll begin this auspicious occasion with the lighting of the lamp. Let's light up the lamp with a great note. So thank you very much for lighting up the lamp. So we'll begin our session from now. I would like to invite our director for a welcome address and also to introduce our chief guest to the audience.
Good morning, friends. It's very rare that we have people like Dr. Radhakrishnan in our campus. So it's a very, very auspicious day for all of us. I would say the campus is blessed today to have a person of his stature visiting us and accepting our invitation, not only to give the talk on the National Science Day, but also to inaugurate a new facility which one of our youngster, Mayuk, has put hands on that and set it up, which is going to be a unique facility among all the IITs. I came to know that this is the first such astronomical observatory among all IITs in India. So that's, I think, let's give a big hand to Mayuk. Such a wonderful job. Thank you, Mayuk. Thank you very much. In fact, 2 years you joined here. Okay. On the day of interview, he said he's interested in astronomy. I said, when are you going to set up your observatory at IIT Hyderabad? So I'm very happy that today, in 2 years, he has been able to come and then get the courage to, because usually it doesn't happen very easily that at your young, early stages of career, think too big and then set up something which is very unique. So I think, thank you very much, Mayuk, for that. So I don't want to take much time. Just let me give a small brief bio sketch of Dr. Radhakrishnan. All of you know him more as a Mangalyaan, the man of Mangalyaan. I think people talked even saying that a mission of that nature, such a mammoth mission, accomplished with so precision and also with such a small budget. So people used to compare it with a Hollywood movie budget and say that it is much less expensive than a Hollywood movie. And so that's possible. As I was speaking to him since yesterday evening, he says it's all because we have wonderful people at ISRO. So this is something that I always tell all of you also. Together, many great things can be done. Individually, each of us may not be very great. But when we come together, a lot of great things can be done. And India has demonstrated this in a number of fields, particularly in those fields where we were denied. We have shown that India is great. Okay, whether it comes to space, whether it comes to atomic energy, and you think of the missile technologies, in all three of them, we have demonstrated that India is one of the best, we have the best brains. And I think that's something, a message that we should learn from people like Radhakrishnan, leading a team which becomes passionate and then delivers what is needed. So I request all of you, we have been trying to talk about interdisciplinarity at IIT Hyderabad a lot. So I would like to see more and more of working together happen. And Atmanirbharata of the country cannot come unless we collaborate together. So that's a message, if there is something that I want to give you today. So let me just read a very long biodata, of course, for a person of his stature, but let me see how I can compress it in a few minutes. Dr. Koppilil Radhakrishnan, okay, is an avionics engineer and a distinguished alumnus of IIM Bangalore and IIT Kharagpur, who is renowned for the illustrious and versatile career over 51 years in space engineering, space applications, management of space programs, and lately in the governance of higher education. And I should tell you, when I was recruited for IIT Hyderabad, he was sitting in the committee. So I remember spending half an hour with him on that particular day. So he is very passionate about higher education particularly. I hope we'll hear something about that also today during interaction with him. Dr. Radhakrishnan led India's first planetary exploration mission to Mars from the concept to fruition. Creditably, while heading India's Space Commission, Department of Space and ISRO between November 2009 and December 2014. Besides, he is also credited with a strong and successful leadership to the team ISRO to execute 35 more space missions during this period. We keep hearing that ISRO does many things which many other countries are not able to do. So some of these, the credit goes to the person who is in our audience today, amongst us today. And also, notably, the induction of Indian cryogenic engine for GSLV, experimental flight test and the advanced launcher LVM-3 and re-entry experiments of unmanned crew modules. Preceding this, he was director of Vikram Sarabhai Space Center, 2007 to 9, and director of National Remote Sensing Agency, 2005 to 8, and founder, director of Indian National Center for Ocean Information Services, as it is called, INCOIS, from 2000 to 2005. And first project director of Indian National Tsunami Warning System, 1997 to 2000, and project director and director of chain of regional remote sensing services centers, and concurrently as the director of budget and economic analysis for the entire space program from 87 to 97 for almost 10 years. At various international platforms pertaining to oceanic realm and outer space, Dr. Radhakrishnan held key responsibilities, particularly as Vice Chairman of Intergovernmental Oceanography Commission of UNESCO during 2001 to 5, and founding chairman of IOGOOS, an association of marine operational research agencies in Indian Ocean to promote global ocean observation system, and as a chairman of working group of the whole, the UN COPUOS and Science and Technology Subcommittee 2008 and 9. Presently, Dr. Radhakrishnan is Honorary Distinguished Advisor in the Department of Space and ISRO, and a member of Space Commission, member of National Security Advisory Board, and Chairperson of Board of Governors of IIT Kanpur and IIT Ropar, and Chairman of the Standing Committee of IIT Council, and Chairman of High Powered Committee in Indian Knowledge Systems, and Chairperson of the Oversight Committee of Science and Engineering Research Board, SERB, and Chairman of Expert Committee of the DST Sati Scheme 2. And Dr. Radhakrishnan is elected to a number of academies, including INSA, INAE, and Fellow of National Academy of Sciences, and Life Fellow of Institution of Engineers, and Honorary Fellow of IIT India, Distinguished Fellow of Astronautical Society of India, and a member of International Academy of Astronautics. There are many more, And I would possibly end with just saying that he is also a Padma Bhushan, one of the highest honors that any Indian can get. And we have such a personality amongst us today. We are blessed to have him with us. Thank you, sir. Thanks for accepting our invitation.
Thank you very much, Professor, for introducing our chief guest. So I just want to tell you that this is a hybrid event. It will be streamed online. So I invite you to give a lecture, and that will be also viewed in YouTube on demand. Right? So since it is a hybrid event, we just have to set the stage for that.
Yeah.
Good morning, Professor Murthy, the Distinguished Director of IIT Hyderabad, Professor Prempal, all the distinguished members of the faculty, all young bright students who are present here as well as in other places and who are going to see this video at a later stage. I'm extremely happy to be amongst you today, especially on an important day like this, which is meant to celebrate Sir C.V. Rao. If you look at the kind of facilities and equipment that this generation is blessed with, we can just go back and see what was the kind of facilities with which such wonderful physics, various areas, was created by Sir C.V. Rao. In fact, this is the first lesson that we need to remember on the day. There's the people, their brain that makes the difference, not the sophistication of the tools that you work with. And the lasting contributions that he had made at that time. Of course, as technology is advancing exponentially, we come across new things. But they were all fundamental concepts which will stay for ages that you create. So as young researchers, young students who are going to do research in the future, think of what lasting thing you can do in your life. Whether you do a research, decide to start an enterprise, or you decide to do something else in your career. Today, I'm going to share with you my life lessons. What you don't see on the internet, what you don't get in the Wikipedia, and many things that you may not see in the textbooks. But this is the lesson of almost 51 plus years of engagement with this wonderful organization, ISRO, and its programs. So I'm blessed with an amazing ISRO and my life lessons. I'll talk about this ISRO and why do we call it amazing. Professor Murthy mentioned about 3 organizations doing great work. Why they are doing great work and why many others, even blessed with greater brain power, may not be able to do that kind of. Number 2, what was the twist in this organization? And if you listen to the bio sketch that was presented to you, you will find it difficult to find out where do you fix me in terms of the domain. So what was the twist and what was the trick in doing that? Domain switching, as we call these days. The last one is certain life lessons. In life, you come across several challenges. As students, you wish to get computer science in one particular IIT, you did not get, you become desperate. And then many things follow. But what can I assure you, something which every one of us will have to go through in our life, career, and profession is challenges, problems. How do you face those challenges? And how do you take it as an opportunity to reinvent yourself and grow and evolve? So some of these things I will share during the course of the presentation and the interaction that followed. Reached out now. And here I'm comfortable here. Okay. This has been the journey of ISRO right from 1962 to 2022. If you go through various documents available on the website, especially that of ISRO, you get details of all these programs. There is a pattern which has come in this. It's a small beginning made in 1962 when the world was into the modern space age. Americans and Russians trying to put satellites around Earth. In a bipolar world, trying to establish their supremacy and technological prowess. There were the intentions of those two nations at that Soviet Union of those days. But in India, when the nation wanted to get into space, here there was a visionary who said, our purpose is different. India was a developing country, so we must make use of space as a tool for helping the development process, helping the way. And this is the bedrock on which Indian space program was built, and that continues to be the bedrock of our thinking process. We had science as the driving force to do research using small rockets in the upper atmosphere from Tumba, which had some special characteristics passing through the magnetic equator. But when you say that we are going to use this as a tool for the humanity, the capability of observation from space, for communications, for observing the natural resources, all became the priority for the mission. So first thing was focus on what we need to do this time. Space applications demonstrate how satellites could be used for helping communication, education, or management of natural resources. Looking at the agricultural field. It was the foreign satellites. Then to know how to build a satellite. You are all having BTechs, MTechs from Indian institutes of technology, university, all around, with a handful of people who probably would have seen a rocket or a satellite, or built an instrument or a satellite. That was the resource pool that was available. But they learned, they were in the 20s or early 30s. They learned how to build a satellite and got the help of other nations who were pioneers in this area. Came the Hyderabad, 1975, first Indian satellite. We didn't have capability to launch, so we launched the Soviet launcher for that. We also had the development of a satellite launch vehicle, and in the 70s, it was a mega project. a very complex project, a large system with which none of us, as a youngster, were familiar with that. But everyone learned together, made mistakes, and then developed the capability to put a satellite in the year 1980. So when Soviets and Americans put their first satellite into the orbit in 1957-58 period, here we got the capability in the year 1980. This was the first step. Then came, how do we build systems that can be used for the country? Came the next set of activities. We must have a launcher. We must have satellites for communication, remote sensing. And we must have the entire nation geared up for using these satellites and their data and change the method in which they have been working till then. That means obsoleteness on the part of the user agencies who are used to conventional service and who had to today use the pictures that come from the remote sensing satellites. It was a major change. And obviously such changes will be resisted when one gets into a technology with which one is unfamiliar. So we had to go through that process. And much of these resource management activities are done by the government system. How do we gear up the government, in the central government, in the state government, to adopt these new technologies? The revolutions that we talk about today in telecommunication or broadcasting, or even getting the pictures from the satellites to look at the weather, or the forest, agricultural field, water resources, all were built through this process of an orchestrated national effort. And that's where we got into the national systems using space technology. If the space scientists remain in islands of excellence in their own world, they would have written papers, published papers. But that would not have reached the fishermen who use today the information coming through the satellite data to look at where to go and where they will get the school of fish. For somebody who is doing the development of watersheds, all districts in the country, we use the geospatial data that comes from the satellites and then decide where I should put a check dam, where I should go for some structural measures to stop the soil erosion. So it is used at that level. At that level, to which you should be able to relate that information to the survey number where they have to put a structure. This is a large national system. We'll talk about it in detail later. Industry. If ISRO decided to build everything within the system, then ISRO would have been a giant organization, which will fall by itself, by its innovation. But ISRO went for partnership with industry. And industry's strength of size, of the engineering capability, of the ability to produce things, all were made use of. And the capacity was available for working for the satellite projects, launch vehicle projects. So industry became partner from the mid-1970s with the Indian space program. And today we talk about in the reforms, the private industries as co-passengers in building space systems. So this has been the base with which Indian industry developed, and we stayed lean from the 80s. Our strength is 60,000 then, but our activities have gone up. And this has been the secret of coming together with the Indian industry. And if India has to be in the cutting edge of technology, where you require the brain power, where does it come from? Academia. And our second chairman, Professor Satish Kumar, an academician par excellence, the director of Indian Institute of Science for almost 2 decades. a student about whom this guide said, Satish excelled me, surpassed me in everything other than age. And that person was Professor Liebman, who was a student of Von Karman. And all of you students of physics or aeronautics will know who is that Karman. Karman line is familiar to all of you. So that is the kind of person who came to succeed Dr. Sarabhai, another inspiring visionary to run the space program. And between them for 22 years, they shaped the ISRO as an organization. And what is that they have given to us? I will talk about it later. So we had programs built around this. Again, focus. The INSAT systems, the Indian remote sensing satellite systems, and ability to launch them from India using PSLV, which we all know today, and the GSLV, and subsea. Now, in the year 2000, India had reached a level where India could launch its own satellites into the orbit, including the GSLV was available. What next? Continue in the path that was set a few decades ago, then it is a sure thing to lead to a stale situation. So everyone thought the aspirations of the nation, the capabilities that we have developed, and the world around us, the way they developed, all came together to evolve a new program that is the lunar exploration, starting with Chandrayaan-1. Just nationally orchestrated. It took almost 3 years for us to study whether we are capable of doing it or not, to convince the scientific community in the country and to gear them up to make use of this data, and also the decision makers that we are meeting in with different. If you read what Dr. Sarabhai wrote in 1960s, we don't have the fantasy of competing with the developed nations and looking at moon and the manned flight, etc. That was written. That was at that time. Probably Sarabhai were alive, he would have got into moon exploration even well before this. So we went, and 2008, India made its mark in a lunar exploration. That was the time China, Japan, all were getting into looking at moon again, because moon was explored in the 60s by Americans and Russians. And there was a period after 1972 when there was no major activity. So a renewed interest in moon came around that time. India was there with Chandrayaan-1, which also helped in a major discovery by joint working with NASA. That's about the water molecules in the atmosphere of moon. So this was a major inflection point. Instead of just going around Earth only, first and even 4 lakh kilometers away from Earth, and also precisely captured that orbit, conducted experiments very well, which produced scientific results. Then came the next step in 2010, where we decided to get into the next step in exploring the solar system. That was the Mars. We'll talk about it later, where we achieved this. Communication, remote sensing, these were 2 elements. Then came the navigation system. You all know about GPS, which is synonymous with navigation. There are several global navigation systems. GLONASS is there, then there is Galileo, Chinese system is there. So India decided we are going to have a special niche. We look at the Indian region and our surroundings using a unique set of satellites at 36,000 kilometers altitude. That was Navi. While we did all this, we were also advancing in technological capability in the communication satellite system. First satellite was specified by India but built in US. That was in the 80s. Then we built our own INSATs. That was in the 90s. We enhanced the power output of the satellites. We enhanced the capability. From a broad beam, we got into spot beams. we got into what we call the high throughput satellite system. This satellite is already in the orbit. We'll talk about it later. And with remote sensing, we enhanced capabilities from just optical to several other areas. That is the next slide which I will talk about. But in the year 2004-2005, we started thinking about human space. There is one portfolio in which India had not got into. Even though in the rest of the areas put together, India was somewhere in the 6th, 7th position in the world in space activity. And that is now seen through the Gaganyaan mission. Then came in 2020 the space sector reforms by the private sector. Enthusiastic, young, tactile minds are getting into making rockets, making satellites, making new applications coming out of all these systems. That's a new area which has come in, and the reforms are providing them the ability to make use of all these ideas and make them practical with the support of ISRO Indian industry, empower, facilitate. And also we have a structure where the operational launch, operational satellite building and their regular upkeep, they are all done by a public sector company, NSIL, where it will be in the cutting edge of space research along with it. So what we did in the morning today, again reaffirms that claim. There are several actors outside the umbrella of ISRO who are into space research, not just being a user of that, but they become the generators of that, who can work with. And I find ample opportunities for such facilities to get into this larger scheme of space research. The wonderful robotic telescope that you have built here today, with the complementary observational capabilities available in other institutes like Indian Institute of Astrophysics or IUCAA or PAFR and such premier institutions who do research in that area to build the instruments which have been flown in AstroSat, which is going to be flown in Aditya mission. And more important, the ability to make new scientific instruments to unravel new problems. If all the engineering science capabilities of this institute could be put together to build a new breed of instrumentation for space exploration, then you will be a major contributor, rather than just downloading data from the ISRO website and writing it. This may take minimum 5 years to get to, and that sustained effort is required, and you will come across a lot of difficulties to have a space qualified instrument with high precision, where things have not been done so far elsewhere. Something unique, first-class science will come out of such an experiment. And that is where I would request you to team up with this scientific institute. We'll talk about it later in the afternoon. Just to give you one example, how in communication, remote sensing, navigation, we have been teaming up and ensuring that this space segment and the ground segment and the user segment, they all go together in harmony, develop together, so that when the satellite is launched, there are people to use it and there are people to put them into practice in the land. This has been a process. Initially, it was demonstration to this country that yes, they are useful. People used to tell us, for you people who are from the space, satellite imagery is like the photograph of your wife or daughter. It doesn't make any difference for us. We are used to conventional survey. And they will say soil is a three-dimensional problem, underground what is happening, you won't be able to see. groundwater availability you can't detect because you can see on the surface. Then the forester will say that my forest is in the slope and your satellite cannot see the extent of it because you will see only from the top. So every difficulty that was brought out, they were all solved, sitting along with them, convincing them, and that process we went through, and that vehicle was what is a national natural resource management system where central government, all the state governments were involved in conceiving what all they could do in their area using satellite. Like how to do that, how to build the capacity in the regular departments who are working with this. And today we have institutions, the IITs, which was built here in Hyderabad, is one such area where in the oceanic realm, how we can make use of satellite. Similarly, if you go to Delhi, there is one for agriculture, in the agricultural department, Ministry of Agriculture. There is one in Dehradun, which looks at the forest act. There is one in Pune, which looks at water resources. And every state government, they have a center where space inputs are getting used for every field of activity which is taken. So this has been a national orchestrated effort by bringing them as partners into the activity to define what is to be built and how to make use of it. Then, those days we were making satellite maps, colorful photographs were available. And we knew that if the color is green in a false color composite, that is vegetation, and different types of vegetation could be identified. A blue color will give you availability of water. Different types of soils could be identified. But eye has its own limitation. So we got into the next level with the signal processing and computing capabilities into digital image processing, using multiple features to be brought into this interpretation process. So this was a revolution sometime in the mid-80s. And we set up these regional remote sensing service centers to ensure that all over this country we have capacity to do that. Then just from looking at the map, we started retrieving the parameters, like sea surface temperature coming out of the satellite data, which finally gets into an advisory to the fishermen to look at where the schools of fish will be. That was another major area. Optical remote sensing in different tanks that was existing, but when there is cloud, you will not be able to see what is below that. And in India, of course, we have clouds in various parts of the country. So we went into the microwave remote sensing at different frequencies, that capability. And the ocean community told we have to have super spectral, multispectral of 3 or 4 bands will not be sufficient for us to decipher. So that was another area. And we built satellites, one for ocean, one for land, one for water resources, one for cartography, and one to look at meteorology, because the scales and the requirements for each one are different. So we optimize the satellites for that particular application. So there is a satellite for mapping which is called cartosat, which can give you or discriminate an object of almost 0.28 meters. That is our one tool. But if you want to look at the meteorological system, the cyclonic system that gets generated in Bay of Bengal and the way it moves to the land, you require scales which are totally different. So that's another class of satellites. So we got into all these areas. We also started becoming international. So in 2012, 2013, we had satellite jointly built with French space agency. Some instruments by them, some instruments by us. Satellites by India, launched by India. And currently what we have is an instrument built by ISRO and NASA too. A combination of radars. What does it show? It shows confidence that the international space community has on Indian cable. And this is also another area where 1 plus 1 becomes 11. We leverage on each one's strength rather than reinventing them and get into the next dimension. So this our habit. In olden days, if you get a satellite data, after about 3 weeks of order, it was considered great. Because we had low power computers to do all the processing. But today it's available almost instantly, near real time. Not simple standard product, but a product with a lot of value added. A product which is defined by the user. Could be ratios, it could be various combinations of bands put together. So this is another thing that India also got into hyperspectral remote sensing. Normally we talk about 4 channels in multispectral or about 10 to 15 channels in superspectral. But here we talk about a few hundred channels, very narrow range. Those are essential to look at specific properties of objects. Of course, the processing methods will be different. So we are in this area on par with any other nation, and probably one of the best with this kind of constellation. In 1995, when we launched IRS-1C, India had the best civilian remote sensing satellite capable. And 20 stations or agencies all over the world were receiving data from Indian remote sensing satellite worlds. So that is the level to which we were known in the world. And today, of course, the joint missions have come. So this is one story. And the last word here is externalization. ISRO always believed that we are doing it for the nation. We are doing it to help facilitate the agencies. Once we develop technology, create institutions where they themselves will be able. And today what we have is satellites are owned by the user agency. If you go to Inauguration in Hyderabad, you will see the ground station of OceanSat 2, recently upgraded to OceanSat 3. They do that business. So it's rather than inward-looking philosophy, we have been looking out. So this is one secret of space applications becoming part and parcel of the value chain of the user community. And if you look at all the nations in the world, this is a model. And every time in the UN Committee on Peaceful Use of Outer Space, we go there, they will ask India to tell something new that is happening in space applications. And that's why we call your role models in space applications, integrating with the user. So, one example I will give. I talked about sea surface temperature. We can derive sea surface temperature from the satellite, the ocean surface, or even from the inside side. A few ratios if you take, that will tell you where the fish is going to be aggregated. Or if you talk about the chlorophyll content, which you will get from the satellites, that also will indicate. You can write good paper, you can optimize it for Indian Ocean, you can optimize it for Bay of Bengal, Arabian Sea. These are all scientific contributions. But if somebody uses this data, then I can find fish of different types. It's also good. Go and validate. You have got a result out of it. But if the fishermen who are going to the sea every day morning, they have to use this data and they have to believe what you are giving is correct. And they have to get benefit out of it. A lot of translational research is required. A lot of communication is required. A lot of convincing is required. And we must know in India we have from the coast of Gujarat to Bengal, almost 7,500 kilometers will be covered by people using 10 languages, English or couple of languages will not work. You have to talk in terms of their own language. If they are using bara, you have to tell, not in kilometers, in bara. So one has to get into the customer. He is a customer for and understand what is the requirement. That is the end of the space application. So there is high technology and science on one side, and there is also down-to-earth application on the other side. This is true for farmers. When we talk about precision agriculture practice or precision farming, finally it is the farmer who should make use of all these devices and finally decide what they should put for his parcel of land. Some information coming from satellites, coming from the other laboratories. So this is a major complex activity. What such areas? So when we talk about Mangalyaan and Moon, etc., this is the other dimension of space activity. This is where we stand in terms of technology. I hope I can take 10 minutes on this. Essentially, we talk about launch vehicles, which of course we talk about rocket science. The other one is building satellites for different applications. What India has today is a set of launch vehicles, the PSLV, GSLV, and the LVM-3, and the most recent SSLV small vehicle. But our ability is to put about 12 tons into a low Earth orbit, about 1,000 kilometers or less. The same vehicle can be used to put satellites in different orbits, but depending upon the size of the orbit, the mass that you can put will change. This is an area in rocket technology where you don't get much input from others. One has to develop from scratch. So we developed solid propulsion technology, solid propellant technology, and created infrastructure in the country to produce solid motors that we use in our launches. Liquid engine, we teamed up with France. And in the 1970s, our people worked in their development activity. In the process, we learned with no transfer of money. They worked there for about 75 man-years and got that technology. We worked on it. And this engine, called Vikas engine, is there in all our launch vehicles. Cryogenic engine was essentially we had to go for more efficient launch vehicles, especially for geosynchronous satellites launch. So we had a problem in the year 1992 of denial of the technology transfer, but we decided to develop that technology thanks to the grit and determination of then Chairman Professor UR. We are going to do it. We are not going to escape doing this by using an inefficient launch vehicle, and we will develop. It took time, but we developed the technology. And the latest one is, of course, getting into semi-cryogenic technology and larger capability. Our satellites, especially PSLV and recently the LVM-3, they launched multiple satellites into orbit, into different orbits. And we have the ability to precisely navigate these launch vehicles and say, the orbit finally what we get is within plus or minus a couple of kilometers. It's an autonomous navigation system. Of course, here you use autonomous navigation for vehicles here. You do it for the rockets which go up. Mechanisms, all these rockets have got several of such things. What you see for separation, what you see for opening the heat shield, etc., etc. These are all done by our own people. All the avionics for locating the rocket with respect to its own reference and then navigating it. And the launch complex. On the other side, in the satellite side, we have a different classes of satellites for different applications. And one of the indicators of our communication satellite is what power you can have. And what is the life of that satellite. What are the frequencies in which you will be able to have communication? Broadband with given footprint or spot beams, which can give larger throughput. All these today. We carry almost 2 tons of liquid propellant in a satellite for its 15 years life. Can we use electric propulsion for this purpose? This is happening. Re-entry from the Earth orbit. It is essential if you talk about human space. Right. If you talk about in the future, we'll bring in something from asteroids or Mars or Moon back to Earth. So that is the capability where things are getting. And of course, as I mentioned on the remote sensing side, land, ocean, meteorology, all these areas. And when you talk about NAVIC system, we had a few NAVIC satellites in the orbit. Anyway, second series is going to happen. And crucial component is the onboard activity clock, which we are developing at the moment. And we have with this for the country assured NAVIC signal. Using the GPS system and improving its accuracy by reducing or eliminating the errors, we have the Gaggan signal, which is used for aircraft augmentation. It's called local augmentation using navigation signals. So all these things are happening in this country today with the space capability. We talked about the organization. What is unique about ISRO that makes all this possible? With the same kind of brain that every other organization in the country gets. So this is the secret. Thanks to the early leaders, the first generation leaders who built. First and foremost, ISRO looks at national priority. We are paid by the taxpayers. Currently, the budget is about 12,000 crores. We have a purpose. What the nation requires has to be fulfilled. The needs of the nation, national imperatives, becomes our priority. And we have a vision, which I mentioned, Dr. Sarabhai's vision. That vision was shared by the entire organization. Application-centric, people-centric space program. But as we evolved, we generated enhancement of it, and that was a shared vision. So initially the vision was shared, and subsequent visions were all prepared together. That yes, we can now look at Moon, we can look at Mars, we can go to human space flight. And finally, the team excellence is the one which makes ISRO different. Professor Murthy mentioned that in the beginning. Excellence of everybody, directed like a magnet takes all the direction, with devotion, with the feeling that we are doing this for the nation, becoming selfless, removing that I from the picture. What will I get out of it? If you remove that and assume that this is an opportunity available to you or provided to you, or that you have got to contribute to the national cause, the whole thing becomes changed. Mangalyaan was done in 4 years. There was another mission in US, which was called MAVEN. It took 11 years from its start to fruition. We started very late, and we were beginners. I had the background of 21 missions and high technology, capability, powerful rockets. But we had 16,000 people who felt that this is once in lifetime opportunity. We all should work together without adding a single hand in the organization. We galvanized everyone's enthusiasm, from 80-year-old Professor U.R. Rao to the youngest engineer who was there. See that, yes, we should seize this opportunity using our own PSN. We should have this mission. It's nice to say, but how to translate that? And that translation is done by all in it. And we learned as we proceed. And then we this comes out of the PNS. And if you see a launch video are available online, you can see several hundreds of people working there in unison. No master has to tell each one that this is your job for the day complete or not. They themselves will. They will sit together and then they will. If there is an emergency, if there is a problem that comes out, a leak comes out in the front, they themselves. So, if required, they will of course come. But the difference is from chairman to the youngest engineer, all are equal when it comes to scientific technical activities. This happens probably only in our place, academic government. And I have heard that Professor Satish Dhawan devised some of these ISRO systems of decision making in technical areas from what he saw in the Senate of IITs, where all opinions are expressed by everyone and a democratic decision is taken. Finally, everyone here together will implement, own it. It becomes a collective decision of the group, becomes the decision of every individual. They will get committed to it and they will. So we have these mechanisms for productive conflicts and then we take decisions. Similarly, when we deal with large projects, we have a structure to do that project. Empowered project management. System reliability and quality are most important for industry. And they are not overruled. If you overrule your quality system, you are sure to get failure. Similarly, safety systems. You would have seen so many failures happening. I will explain some of them later. Failure resilience of the organization. When a rocket fails, you will see all the people coming together and discussing on how it could have failed. They also will say, next rocket we will bring in 6 months. We will work together and they will bring it and that will become a success. So this resilience and learning from the lessons of success and failure. Missions may be success, but many systems would have underperformed. We locate them immediately and then correct them. Transparency and accountability, as I said, it is taxpayers' money. And we have a responsibility to communicate to them what happened. So this happens. And of course, when things fail, the leader takes responsibility. Not that gentleman did not do his job, I was doing, but he did. He never said that. The leader showed his responsibility. Now, much of the story that I explained to you is available in a book. This is a book from Fishing Hamlet, that was Tumba to the Red Planet. This was published in the year 2015. When people write history, history will be always colored with what the persons in power want to project. But here, we made a difference. We got all those, you created history, all those leaders of all those to write on how they got it. And for some of those people who are not with us, we had their own interviews, etc. So we had how Vikram Sarabhai got into, how Professor M.G. Menon came there and started some other programs. And each one of those leaders articles in their own ways, including some of the youngest people who are running the show at the moment. They are also there actually. I also got a position there to view my version. This is called India Space OTC. If you want to have further reading, catch hold of this book and that will tell you the journey. Now let me talk about my journey. It's quite simple. I joined in the year 1971 as a design engineer. Did my MBA and then came back, started looking at systems in avionics area. For me, it was an enhancement, widening my horizon. I moved into ISRO headquarters where I started looking at the entire space program, even though I was a young man at the front of the line. But this was about 13 to 14 years of my life. Then we had a session with Professor Satish Dhawan. He was my mentor actually. we spent a few hours how one can widen the horizon. Rather than becoming a facilitator, how you start doing, delivering things. The responsibility for me was to set up a chain of regional remote sensing centers for the digital image processing in various parts of the country. That's why I got into IIT Kharagpur. Essentially, my job was there to translate a vision which was handed over to me. And I was in my early 30s, but in new domain, I did that job. Then also, I realized that in this area of science and technology, if you have to grow, you must also have a doctorate degree. Degree is one part of it, but how you earn that degree, what you learn during that process is important. So I went to a tough place, that was IIT Kharagpur, and you know how IITs look at the research student, research scholars are there. So I wanted to do it in my hard way, go through the residency program of one term, sitting with the students who told my father is of your age, but still I had to excel. I had to keep on par with them. And some of my professors are retiring only now. They were quite young at that time. But I was a student, and they were my teachers. I went through that process. What I gained during this process is what is called learnability. And I decided that I should be an excellent student. My work should be first class, because otherwise my juniors also will laugh at me. That was a challenge we faced. So for the last 20 years, I am able to read, study, new things all came out of this. Then came the challenge, go to ocean from space and develop a new center that is there in Hyderabad today. It's a new challenge. A different environment, not a protected environment of space with all its culture and the systems. A conventional department which was just coming up and rocky areas in near Kokatpalli to build that system. Here what I did was, instead of becoming just a notional data center as it was envisaged originally, we decided it should be a knowledge and information enterprise for the oceanic realm. This vision, a redefined vision, was accepted by our men. And we also decided that if an institution publicly funded with the taxpayers' money has a reason to exist, it must have a relevance. It must make a difference. Otherwise, we have no right to draw salary from that. So with this, when we started, we made a difference, not only in India. The globe started looking at different. So for several things, for India, the global oceanographic community started looking at equality, even though we were only 4 years old. 2004, we had the tsunami. It was unknown at that time. What is tsunami? Except people knew the definition of tsunami. And then what happened was, there were several experts looking at different elements of tsunami and coming on TV and talking about it. But here there was an organization where everybody said, now this is an opportunity. We must seize that opportunity. And we must live up to the expectations of our people. And then we became the Tsunami Warning Center and the responsible national agency for tsunami early warning we described. So this is something we did. Rather than making some publications out of all this, saying that yes, we have understood tsunami will come in India also, Indian Ocean also. We create an organization. Today it is the Tsunami Warning Center for the entire Indian Ocean region. So that is the level to which we go. Of course, I went back to National Remote Sensing Agency. For me, it was again going back to my family in the year 2005. But then we created something for the future. In Sharanagar, which is very close to this place, we had 320 acres of land. And the ground stations were. And generally, people who are transferred to that place were not very happy to go there because they had to commute every day 4 + 4 8 hours to reach that place. and then be there for 24 hours, looking at all the ground equipment and see that all data is received. It is a resource for us very close to the new airport for us. So we created something new, a marvelous system. In olden days, for each satellite that was in the orbit, you had to have a ground station. Built a new, and most of the time it was not getting ready on time. Softwares had to be developed, so we had to wait for them to be tested to get even the first product processed. So we created a new technology, an integrated system which is versatile, which is flexible, and which will provide the processed output to the user in just a few minutes time. It's available. The whole place has changed that. It's a good showpiece today, and good asset for the entire space community. So this is what we created. I had to go back to Vikram Sarabhai Space Center. My place after 26 years. I just wanted to say, this learnability that I got from IIT Kharagpur, continue learning with the youngsters. So when I went back after 26 years, with a new generation sitting there, with at least 650 who were in their 20s, I had to change myself. I had to connect with them, and I had to learn new things to even talk to them. So I had 15 youngsters chosen from all these disciplines, and we learned together a lot. They learned something outside their domain, and I learned through them. So the learning has different ways of doing that. In an academic institution, certainly, I'm sure the professor will learn from the students also. Of course, in ISRO, it has been a different game, leading this large number of people. Not only running the organization, because there is an external world to which you are responsible, the nation to which you are responsible. You represent the nation. And there were several challenges, some of the challenges. First year of my chairmanship, I had 2 failures of this. First one was the testing of the cryogenic engineering stage, which started in 1992. Many thousands of people had worked it, and that's a dream of everyone. And first test, everything went ignited. The cryo thought it is now going to work, but it stopped. Less than seconds, 800 milliseconds it worked. Then we had to find out what happened really in this situation. It took time for us, and we knew that it is going to take time. So we had an available Russian cryogenic stage. In December, we flew with that because we had to build satellites in orbit. That failed even in the first 45 seconds. And we decided to give a command to destroy the vehicle at 53 seconds. It's a ground command. And the people saw it as a big explosion. Even today, if you search for Dr. Radhakrishnan, you will see this picture what you are seeing on right side. Because our people celebrate failures rather than the successes. So these two happened. And then, of course, the associated criticisms all will come. Our team worked to find out what was the problem. Then we found this GSLV itself had many failures. All the problems of that vehicle was unearthed. We went to the launch pad in August 2013, 19th August 2013. We looked at with great detail all that modifications that we had done. Then we found in the otherwise properly working stage, one leak started just 1.5 hours before the leak started. 1 ton of propellant, actually the fuel, had leaked. And it is hypergolic. Would have created havoc for us. So our people unearthed immediately, and then we stopped, we aborted the mission, and we had at that time hydrazine at 5,000 ppm, where the allowed number was below 1 ppm. Otherwise, one could have irreversible reactions by human body. And we had to save that vehicle and bring the vehicle back to the vehicle. Just 2 weeks work of about 400 and odd people. And we all had to be in the front. And that is what really is the leading from the front. We did that. We saved that vehicle. And we made the modifications. And in January 2014, we had the successful mission with the Indian Cryogenic Agency. Subsequently, we had half a dozen successful flights. Now imagine you are the head of the organization going through this process. What will be the state of your mind at that time? And what kind of grit and determination one has to develop? And what kind of dispassionate looking at the situation? If I start looking at whether I will get an award, if this is successful, then I will be only worrying about the award, nothing will happen. So you have to live in each moment of time and take action what is required. And the entire team will be looking at the seniors at that point. So that is where the mindful decision making comes into technology. And to come out of it, what may be the result? Even this also could have been a failure, but then you have to tackle it. Because people tackled such things in the past, we have space technology of today. Then, of course, we had a new A3 first flight and all these things happened. But the point is, in this area, if you are working, you should be ready for success or failure, what may come. Sometimes we look at Bhagavad Gita program. In my first launch failure, after explaining everything, one of the correspondents asked me, how do you feel? And I told Karmanya you concentrate on your work, don't worry about it. So if you are a PhD student, you should be able to have a classic PhD thesis. Not worry about whether I will be selected for the best thesis and I will be given a medal in the convocation. That should not be your aim. It should stay for years. And your guide should be proud and it should result in several new problems to come. This, of course, is what we meant by team excellence in Mangalyaan. These are some of the life lessons which I learned. I think my time is out now. First and foremost is widen one's horizon. And some of my colleagues from Kanpur told me, or their guide told, don't continue the area in which you did your PhD and your postdoctoral research. Get into a new area. And if possible, 10 years, get into newer areas, that is a way to keep you up to date. And as someone said, if you climb on one areca tree, you swing from there to the top of the next tree. You don't again come down and go up. So this is the facility available for all of you. Having mastered one area, you can easily adapt to another area. Raise conceptual skills, see the forest. Some people are very good in counting the tree. Some people are very good in climbing up and down. But if you want to see also the forest, which is important. So that conceptual capability in your technical area, scientific area, or in any other area is important to develop. And of course, sense and prepare for opportunity. What I mentioned about tsunami was one such. Embrace adversities and tough targets. Both the GSLV example, which I told, and the tough targets. And we decided to get into the Mangalyaan mission in 2010 June, when we had already had the failure of cryogenic. That is the time. So when time is bad, time is difficult, look for tough targets, high targets. And if you can achieve that, you will be back as an individual, as an organization. Encourage critics at all levels. This is very, very important. You must have people who will question you, whether it is close, good friend, sincere friend, competent friend, who wants your good things to happen. As an organization's chief, I expect my first level colleagues to question, to ask questions. At the end of it, you will get something which is far, far better. Otherwise, the organization will be led by my ignorance and my weakness. If I take everybody on board, we are together, we will be leading with the excellence of all time. And if you don't take criticism positively, if people sense that the boss wants to listen from you what he likes, that he is great, then I can assure you, they will lead to the garden path, into the pond, and then they will laugh when you fall. So look for honest critics, whether it is your friends or anybody else. Gain stakeholders trust, whether it is the customers, whether it is the government, whether it is the people. They should believe you. Don't try to hoodwink anybody in a business space. If you are rich, have the courage to win business. Foster team excellence, I mentioned that. Not only telling team excellence, when you give an award also, you should ensure that the team is recognized. Everyone in the team is recognized. Of course, enrich vision, sustain, focus. There are some PhD students, they would like to do everything. If you are a PhD student, looks at like this, then they may not look at any problem. But you have to focus and find out what you want to really achieve. Accomplish and make a difference. At the end of it, that is important. And developing the new generation is your responsibility. If a leader says that I got this organization in bad condition from my predecessor, and there is nobody below me who can take this organization forward, then he is a failure. If he is a successful person, his absence should not be, or her absence should not be felt. And live with a legacy. Everyone will not be fortunate, some will be fortunate to have that legacy. Share, care, mentor. This anybody can. Having got things up to certain part of your life, this is the time for us to share and care and mentor whatever we have. So I am in that stage of life at the moment. Thank you very much. Thank you, thank you. You will go by what you say now.
Yeah. Anyway, so thank you, sir, for a very interesting lecture. So this is perhaps one of the biggest crowd we have seen, at least I have seen. I'm sure that everyone would definitely have enjoyed it. There's a lot to learn from your life, and I'm sure that our students and the younger generation would get a lot of inspiration out of your talk. So we have a dedicated faculty interaction with our chief guest. We have a little more time, so I would rather take questions from the students. Any questions, please? A lot. Yeah?
Only the students, please.
Only students. Pass the mic.
Somebody can carry a mic.
Very good morning, sir, and thank you for giving this opportunity to ask a question. And sorry, as my question is little longer. Sir, being a leader, leading a highly ambitious mission, it seems to be impossible. And in a nation where people are fighting for the basic necessities, and as you mentioned in your the lecture that you are working on the taxpayers' fiscal responsibility. So, like, sir, each and every day, what kind of mental challenges you go through, keeping in mind that critics are there who are criticizing that instead of using that money, we can use that money to for improving the basic and providing the basic necessity to the nation like health and education. Each and every day, what kind of mental challenges and fear you go through, and how you deal with it, and how you motivate yourself and all the scientists and engineers.
Thank you, thank you. And Dr. Sarabhai suggested that we will do a space program. People asked, why are you spending good money for this? That was the 1960s. And he stated, what is that vision? That is people-centric space program. This question will continue to be asked all the time. When 2013 we had the launch of Mars orbiter launch, there was an India Today conclave in April-May 2014, where the subject given to me was rotis or prophets. Very relevant subject. And they got the chief of French Space Agency asked me questions. Why are we doing this? But they were disappointed. Because in India, rockets are required for more work. The kind of thing that I mentioned about the use of remote sensing for agriculture, remote sensing data for early forecasting of the crop production, for better policies of import export, etc. For giving that information to fishermen in this country to go and find out where the school is. Thereby they can reduce the use of diesel or petrol, etc., free of cost. These are all happening in the country. But we need to continue to talk. When we have high technology missions for space, one of the outcome of it is the spin-off technologies which could be used in several areas. Today we talk about telemedicine in a big way. Where did it start? It started from the space program because the astronauts had to be monitored. Where did remote sensing come from? Astronomy. Astronomers were looking at the sky, and then America wanted to find out where they can have landing sites in. They used some instruments to look at moon. That was translated to looking at Earth. It became remote. So people asked, what is that you are going to get from Mangalyaan, for example? Mars orbiter, Mars you go and orbit. We are not going to live there also. It takes 1,000 days to go there. Now, if you look at Mars, there are some technological spin-off from Mars mission, which comes to every satellite operation. For example, because of the geometry between Earth, Sun, and Mars, at least a couple of weeks, ground controllers cannot dialogue with satellite. So satellite has to manage by itself. That means you bring all the decision rules on the ground into the satellite, and satellite has to make flawless decisions. So we built this 8 years, it worked. So now our operations of the other remote sensing communication satellites have become far more efficient because. And who is the beneficiary? Long life of the communication satellite. That means in economics, you'll get better rate of returns. So these are all the benefits coming out. This is the first part of your question. The second part of it is in every organization life is different. It has its own challenges. As you grow higher and higher in the organization, your responsibilities will become more and more. So that is your duty, the task given to you, do that job. It's a platform in which you have to perform. If you look for that as a platform for doing something bigger, then you will do great things. If you think that is my aim in life, there is a problem. If you are the 9, 10, 11, 12 standard things are getting through JEE is my target in life, you will get into IIT and you will stop studying. But if this is an opportunity for you to get into new frontiers, that person will become doc, postdoc, etc., etc. They will do something great. So this is how you look at it. So in every place there is a challenge. Your teacher also will be going through the challenge every day because they have to teach new subjects to new set of students, to enlighten students. So everyone goes through that challenge. So be ready for challenging your profession. You get it.
Morning, sir. My name is Harshal. So as we can see that the flight that ISRO has taken in this last years, it has been really overwhelming to see. So one thing I want to ask that for sustainable mission, how we are going to deal with the space junk that being as a collective humans we are creating, and how ISRO aligns its goals with that.
That's the concern of everyone in the world today. Because we have operational satellites which are doing great service. And our life is today dependent on many of the provisions available through those satellites for human well-being or even national security. And there are at least 20 to 25,000 objects which are in these orbits going at very high speed, even though small in size, they can create harm. So the anthropogenic debris that is created by the human operations is one area of concern. Second area of concern is the cosmic debris. We talk about meteorites, etc. It's far more difficult to handle. So first and foremost, you should know where it is actually. So there are ground observation capabilities. US had it, India is building. And then ability to model their movements, to see whether they will collide with any active operational satellite. And if that happens, how do you, like in traffic management, how you manage those operational satellites? It's the regular service. We have a center in India, in Bangalore, near Price. The next one is many of the objects, bigger objects. They may come down, but at that time they may get diffused. But some could fall. So how do you study those objects? So globally, these are being studied. In fact, every year there's a competition. They will identify an object and 6-7 participants will continue to model it, and whose prediction comes true, etc. will be seen. India has a good status. What India is now doing is the capabilities to track those small objects. So this is one part of it. But this problem doesn't stop there. How do you reduce them? How do you scavenge them? So there are a set of technologies getting developed using kind of net kind of configuration for catching them. This is happening. The second one is guidelines and regulation of such things. Many debris will happen naturally because of disintegration. But many debris happen because of intentional attacks by owners, like China, who did it recently. So there you can only talk properly. So this is also happening. But bottom line is space situational awareness has come as a very major discipline in the civilian domain. The next one is space domain awareness. If your hand falls on me, that is one part of it. But if that is with an intention to hurt me, that is the second part of it. That's space domain awareness. These are two areas developing fast. So there is technology, there is computation, and there is also regulation. Yeah.
This was very nice talk and inspiration as well. Then my question is, as you are saying that we should also celebrate our failures, right?
Not celebrate. Embrace. Don't run away.
Once suppose you are getting failure or anyone is getting failure, then how one can make their mind to let's start once again. Let's restart work and work on that.
See, I am standing before you because I have gone through several failures, not only in the missions, in life also. So when there is a hurdle in front of you, there are 3 courses of action that you can take. When you get depressed and do all associated things, some people go. Some people will float around. But if you can use that as an opportunity to disprove those things, then things will be different. At that time, it is difficult to live through it. Disprove your work. Once you achieve that, even those people will etc. I said I moved from space to ocean. But when I got into the ocean, the challenge was to prove it a new domain. And it is a very detailed process. So if you read my book, my VC, I have written that portion. Why I moved into ocean, what I faced in the ocean, and how I came back. Just to summarize it, Professor U.R. Rao is a very well-respected scientist and known for thinking on the face. So he told me, when I was chairman, he was giving an award for completion of so many years. He told, when a coin goes on circulation, it comes back losing its shine. You understood that, because many people are angry. When Rand came back, he gave it more shine. So now you got your answer. So that determination should be with the fire in you. Every day I have to prove that yes, all those people who criticize that I'm useless are wrong. For that I must do extra work. So you thank them that they have given that verdict to you because of that you performed at a higher. Otherwise you would have been complacent, you were in your comfort zone, you would achieve certain level, that's all. So who takes you out of that comfort zone? It is the one which is. That's why I said in your area also you get out of your comfort zone. And you will excel. Initially you will go through. In nature, transplantation of paddy, have you seen? If it is in the nursery, it continues to be, it will get stunned for some time. So transplantation will create that yellowness for some time. After some time it will. This is a natural process. And
thank you very much, sir, for hearing many questions. Now it's time for bringing the guest. I request our director to please come on the stage and give a small moment as a token of love to the chief guest.
Thank you. I express my heartfelt thanks to our chief guest, Dr. Radhakrishnan, former chairman ISRO, for accepting our invitation and for being here with us today. Sir, your thoughts have inspired us. And I would like to thank our director, Professor B.S. Murthy, for always supporting and guiding us. Sir, I appreciate your dedication and commitment for the growth of IIT Hyderabad. And I express my sincere gratitude to Director Office, Admin Office, Guest House, Raghu, PRO, and for all necessary support and cooperation. And special thanks goes to CMD and for their excellent work because they made site ready in a very short time to get it inaugurated on this special day. Really thank to that CMD team and the associated staff. And I would like to thank a team of faculty, staff, and student volunteer led by Dr. Niti and Dr. Anupam for their unconditional support and hard work for making this event a grand success. Finally, a big round of applause and thanks to all participants who made this event a memorable one. Thank you very much.
So, welcome back. After hearing a very interesting talk, we're going to have another very, very interesting talk. And it's my pleasure to introduce, I would say, one of my mentors too. Sir, can you hear me, please?
Yeah, I can hear you. I can hear you, please. Yeah.
So nice to see you, sir. Yeah, it's my pleasure to introduce Professor Prasanta Panigrahi. He is professor in the Department of Physical Sciences at IIT Kolkata, and he is also a current director of IIT Kolkata. Before joining IIT Kolkata, he was a faculty of the University of Hyderabad as well as Physical Review Laboratory. His area of expertise include quantum computation, quantum information, physics of cold atoms and molecules, nonlinear dynamics, quantum field theory, wavelet transform, etc. He is a principal investigator in the prestigious project Quantum Information Technology with Photonic Devices under the Quantum Enabled Science and Technology QuizSet of the Interdisciplinary Cyber Physical System ICPS, a program by the Department of Science and Technology, Government of India. He is an international project evaluator for National Science Fund, Swiss National Science Foundation, National Academy of Science, Ukraine, National Research and Development Agency, Chile, and National Project Evaluator for SERB, BRNS, DST, Indo-US, and so on. So he's almost a reviewer of many funding agencies. He is also a reviewer of prestigious journals like Physical Review Letters, Physical Review A, B, Journal of Physics, Physical Letters A, and European Physical Letters, to mention a few. He is also on the editorial board of Prayas, Student Journal of Physics, Physics Education, and Discrete Dynamics in Nature and Society, Journal of Quantum Information Sciences and Atom. He is a fellow of National Academy of Science as well. So indeed, it's my pleasure to invite Professor Prasanta to please take over the stage and give his talk on emergence of quantum science and technology in the 21st century. Thank you.
Thank you, Niti, and thank you, IIT Hyderabad. And I do see Bandana, are you around? Hello, and many of my own people.
Yeah, I'm there.
Yeah, let me share the slides with you. Yeah, I don't have to do anything, right? So you can imagine we are talking about quantum technology with this classical computer, which still has creates problem for me. Okay. So emergence of quantum science and technology in the 21st century. That is the why is it not visible? Like what happened there? Why this other slide is not visible? So I think we can go. Not next. That's it. Okay, so let me get going. It's okay. Yeah, that's perfect. Yeah. So first of all, I really am thankful to IIT Hyderabad and Niti, Alok, and others for inviting me and giving me this chance. And you know, for example, I would specifically say Hyderabad has emerged as a very nice center for quantum computation. At Hyderabad, for example, you have some good number of people. Alok is there. IIT Hyderabad has both in quantum chemistry, where, for example, Harjinder Singh, Professor Harjinder Singh has really used quantum computer to calculate energy levels of molecules. And then Arun Patti has joined there. Earlier also, there's a strong group there. And if you see DRDO, so Hyderabad University, it has really come up as a very nice center and very nicely balanced between computation, algorithm, quantum optics, and whatnot. So today's talk will be basically motivational, and I will basically tell you some stories, try to motivate you. Okay, but let me also advertise that there are many workshops which are coming up. For example, we have one workshop starting from May 8th to end of June kind of thing, where lots of speakers from all over the world, some mostly online and offline together, will be joining. And you are welcome to join, and no money and all free of thing. So this 21st century, as you know, for example, there was no need for quantum technology or quantum science until now. Why was it so? Because if you send your rocket, you need Newton's law. Now, for example, if there are many degrees of freedom, statistical mechanics, thermodynamics, for example, chaos, those are the kind of things we have been dealing with. Newton's law and Maxwell's equation, those have been enough. When you need a bit of nonlinearity, for example, Nikki talked about his area, that is nonlinear science. So you encounter nonlinearity, use it for technology, optical fibers, solitons. And so those are the kind of domains which people have been concentrating. Really, there was no need for any quantum. And need arose slowly starting from 70s. So since there are beginners, let me tell you about how I'm going to progress. And it's a recent progress I'll highlight to you. And I'll introduce you to quantum computers, basic ideas. And this timeline is one which I'll use to tell you some stories about why we started, and what is the fundamental building block, which is a qubit. Give you some physical idea about that. And basic principles, there are many other kind of things that are possible, but the two key principles are superposition and entanglement. And then getting into quantum computers, there are various platforms available. What are the main technology I'll highlight? What are the basic gates? The people who are using one classical computer, they know different kind of gates are there. that you can use in an architecture to carry out your operations. So similar kind of things what are there in case of quantum, I'll emphasize. This is basically for the beginners. I apologize to the experts because for them that is probably not much to learn. Now, no cloning theorem, I'm just emphasizing that when you do quantum, certain things you have to keep in mind. For example, an unknown file, you cannot Xerox it. You cannot make a photocopy on an unknown file. Known things, of course, you can create. And similarly, you cannot do things faster than light, no signaling. So, and there are small things of that kind which you have to keep in mind. All those things arose, please keep in mind that quantum operations have to be done through unitary matrices. So keep that in mind, unitary. So, whatever you can do through unitary matrices are the things that is possible in a quantum computer. All other non-unitary processes are nuisances. They create noise, you lose information. So that's the main point. So to sort of tell you the timeline story that these computers, as for example, after Turing gave this idea that you can have a so-called Turing machine, where essentially you use addition. That mod 2 addition, 0 plus 1 and 1 plus 0 being 1. 1 plus 1 is 2, which is 0. So this mod 2 mathematics, Turing pointed out, is enough to do any kind of computation. So subsequently, von Neumann came up with a real physical architecture where you have 0 and 1 in the form of electrical voltage. No voltage is 0, some amount is 1. And keep on adding more complicated circuits you can build, sophisticated language, now the high performance computing, for which Hyderabad, your IIT Hyderabad is very well known. You have a very powerful computational things, particularly in computational science. IIT Hyderabad is very well known. And so those are the kind of things which we have been doing. But when these things started becoming smaller and smaller, in 70s, real engineers encounter problems. A lot of heating up going on. And then information is getting lost. There is a very beautiful result which this person Landauer, it's very fascinating if you look at it. He found out that half KT information loss amounts to erasure of 1 CBit of information. So this language like CBit, I also learned as I went along because many of these things I myself do not know. There is something called Holevo theorem. That was also 1970s. And the people who do quantum information science like Alok and others, you will find Holevo theorem. So when you measure how much of information you can extract, it's a very profound paper. I was not aware about it. Holevo theorem, and many of you should read it. How much of information you can extract? Because finally you have to interpolate and interface with the classical world. So once classical bit of information is all that you can extract from a given measurement. Very profound. You can store so many things, but to extract is not easy. That has created a lot of problems. Basic understanding of quantum computation comes through measurement. Keep that in mind. Rest are all matrices you can do through your MATLAB. So therefore in 70s, when they encountered, the first result was that heat loss is information loss. And very precise, half KT is 1 CBit. Then came...
Yeah.
Am I audible?
Yeah, we are hearing you very clearly, but your slides are stagnated. We are not
So the slide is not moving, sir. So it is actually we are still on the slide number 2.
I am actually telling some story. I will move on a little later. So I'm just telling the story about the beginning, then I'll get into slides. Right now, I'm not deliberately moving it. I'm telling you a little bit of story, introduce you to the need for quantum computer, then I'll get into third slide. So this is basically I'm telling you about the timeline. That in 70s, people encountered problems because chip size was becoming smaller. There was a lot of heating. So that led to real problem and understanding of thermodynamics and information. Then you will see that in 80s, how Feynman and others came, and then how the quantum computer developed. But the encounter was because of electronics people encountering designing chips, heating problem, information loss. Okay, so now let's move on to, so where are we now? So as you know, this 2022 Nobel Prize was basically for people who did quantum optics to prove this Bell's theorem. Now, if you look at it, they are very difficult experiments. Now, of course, people do it routinely, many places all over the world. But those days were very difficult. And I remember when I was doing my PhD, Professor Mandel's lab in Rochester was one of the labs where a lot of original results came. Aspect was in France. And Clauser, for example, didn't have a job. He came up with this part of the CSHS inequality, which he checked using light. Giling also the same thing. So these are the people who used light to show this quantum non-locality is present. So quantum theory is non-local, intrinsically non-local, and that came by looking at the so-called entangled states. Now, people who are from physics or electronics background, you would realize these are very simple states in some sense. For example, singlet state in helium, the 2 electrons, they're in a singlet state. Hydrogen molecule, the 2 electrons, they're actually in the so-called Bell state. So similarly, if you have a pi naught measure which decays into 2 photons, they come out in a Bell state. So Bell states are encountered in nature. They artificially created those kind of states. They pointed out that it has some non-local correlation, which I'll describe to you more physically. So these experiments really showed validity of quantum mechanics, absence of the so-called hidden variable theories, and quantum non-locality being real. Only thing is that nothing you can do faster than light. Very careful experiments. And you realize that this year's foundation prize also has come to 4 people who are into quantum algorithm. Yeah. So that some of you are curious, this is basically for experiment, that is for algorithm. Okay, so now quantum computers are available. Many of you can play around, this, which we have also played around using IBM available pieces. Here is an experiment, which was done using 9-qubit platform. Don't get into details. There are a lot of debates going on even now. Essentially, the year Einstein, Podolsky, and Rosen EPR paradox was given, the same year, Einstein and Rosen, they showed that there is a theory, solution of general theory of relativity, which allows you to come up with so-called wormholes, which can connect one part of the space-time to the other. For example, imagine if you are here going to Andromeda, it may take a lot of time. But if you can dig a hole, so-called wormhole, you can connect it faster. And what these people have shown, that there is a way of showing this thing in a quantum computer, 9-qubit, which they showed experimentally. And there quite a few things were used. For example, originally, you need a lot of qubits. There comes a BTech student who showed using machine learning that the whole thing can be extracted using only 9 qubits. That made this experiment possible. Then there was a model called SYK model, Sachdev-Yekitai model, which has duality, namely showing this equivalence to this anti-sitter, de-sitter space. So that was used. So quite a few non-trivial ideas were used to show, quote unquote, that a wormhole kind of solutions are possible. You can show it on a quantum computer. A lot of debates are going on. Please check it out. And but main point is this: it showed essentially something called teleportation. Teleportation so a model was realized. You can see now people, for example, are really looking at molecules, finding out the energy levels. For example, I mentioned about Harjinder Singh from IIT, excited state energy levels, ground state levels, very accurately using quantum computers. SYK mechanical model or ITC kind of high temperature superconductivity. So those kind of things you can actually check out. For example, on a quantum computer, and they are actually reliable. So therefore, this kind of concept, which leads to exotic ideas being realized, is one example. So this has obviously led to a lot of debates. People are contradicting. There was some comment only last week. But main point is that people are attempting non-trivial things. Okay. Now, where are we in India? This report I'm quoting is 2019. You'll be amazed to know, as a country, we have highest number of graduates in quantum technology relevant fields. This is McKinsey report, 2021 numbers have changed. We are still having the highest number of graduates in quantum technology relevant fields. And European Union as a union, they have a bit more, but as a country, we have the highest. Now you may wonder how come we are doing reasonably well. Because younger people, for example, are really interested into doing quantum computation. They have taken Coursera courses. IBM has regularly conducted schools. Many of these kids have learned QSKIT platform. There are 8 of them sitting right here. Next to me, they know how to handle quantum computer better than me. And you can actually do non-trivial work. Government of India has given access to many platforms through MAITI, giving some money. So now the quantum computers starting from D-Wave to IBM are physically available. And training, for example, a lot of people are trained. For example, I just heard from this IBM Indian chief that many of the high school students have got certificates. that last around workshop they conducted 2,000 high school students. Similarly, in our conference, as I mentioned to you, we get large number of participants who may not be knowing all of it, but basic ideas. Main point to remember is that the technology in such a phase, if you know matrices and understand measurement, you can contribute non-trivially. Okay. So now I can tell you what is the startup experiment. Alok knows he's a part of it. Many of us are. Government inspired, government gave this program for Quest, Quantum Enabled Science and Technology. That brought a lot of Indians together. People came to know what each other are doing. There was collaboration. You see, one of these very nice results that a very beautiful experiment was done by Professor Radhakrishnan with early work, one of the early founding workers on quantum information theory, Professor Dipankar Om from Bose Institute. And this was loophole free. See, this word, of course, it was not Bell inequality, it was Leggett God. Bell inequality is about quantum correlation in space, non-local correlation in space. For example, you take a singlet, the two electrons in a helium, they are located in space. So this non-local correlation in space. Similar kind of correlation in time is called Leggett God. It was given, in 80s, Anupam God and Tony Leggett. So these kind of experiments are very tricky, both Bell and this. You have to do something called loophole free. When you test, there are a lot of counter examples people can give. For example, Bell test. People claim human consciousness can affect it. So the last experiment which came up with this loophole free was from Barcelona, IPFO. They involved something like 100,000 of volunteers. It's a Nature paper you can check out, 2016-17, from many countries, 13 or 14 experimental platforms, just to show that Bell inequality is independent of different kind of experimental platforms, different kind of people, different kind of time zone. So that kind of, the limit people are going to show that this correlation exists and it is non-local. Now this experiment was done, a very remarkable experiment, because first of all in India, we are, we're not all that great in experiment, you can check that, but this is a very beautiful experiment. Devashish Shah was a BSM student from here. IITs, for example, early on have gotten into this quantum computation domain. Devashish did an MS project with me, for example, here, went to Goa. Now he's in IITs Thiruvananthapuram as a faculty. And so this is a very beautiful experiment and a very reliable experiment which has come out of India. Okay. So now, as I told you, many people are yeah, hello? Many people are contributing to quantum computation from different branches. So this person whom I am showing, Urmila Mahadev, very basic question was asked. Suppose somebody has a quantum computer. How do you show that it's a quantum computer? This question arose because there was a very powerful computer, D-Wave computer, which was a Canadian company. You can check out their website, D-Waves. So they solved many problems. Now, what were they using? Were they really using quantum principles or some other, wave phenomena, some other phenomena, some kind of other correlation to solve it? So this field arose that quantum verification. If somebody claims that I have a quantum computer, how do you verify it? Essentially, you have to ask questions. The quantum computer should give you honest answers in the form of like, plus minus 1 or minus 1. Looking at the statistics, you would claim that it is quantum. So those kind of things, for example, if some of you are familiar with optics, quantum optics, you would know that, the statistics kind of thing through which one infers about the quantum nature of matter. Laser light, for example, is classical. It's called coherent state. Because if you look at the distribution of the photon, it satisfies so-called Poisson statistics. So by measurement and measurement statistics, you can quantum nature of the process. So Urmila Mahadev was a student of Umesh Badirani, University of Berkeley, California, Berkeley. 8 years, one paper. And if you read the paper, you can actually infer that it is a quantum computer. So that really proved that D-Wave is a computer, quantum computer. Before that, you could check a lot of debates. People will ask D-Wave is not a quantum computer. D-Wave people will do more painstaking things showing that it is a quantum computer. There are a lot of exchanges between PRL, nature, and science, and the conclusively shown that these kind of things can actually prove, and that's a quantum problem. It's a quantum verification problem. Now you can check out. See, I think is a faculty now in Caltech. So therefore, you see, he's a computer science person who understands what is measurement statistics, and that's enough. You can do good work in quantum computation. Now, I mentioned to you about another small problem, because many of the students who come here for project, they will claim I only have done some first year, second year. I am hardly 28, 20 or 21. How can I do quantum computation? So I give them this example. This girl is doing her PhD, I think University of Washington in quantum computation. At the age of 18, for completing her high school, went to Sorensen in University of Texas to do a project. She was told that can you solve this quote unquote a quantum Sudoku problem? Sudoku she used to like. So the problem was this, that there is a matrix like a Sudoku where some entries are given, numbers, others are missing, and you have to fill up only with two information, that this matrix is low rank and most of the elements are non-zero, namely non-sparse. Most of the elements are non-zero, that is understandable. Low rank means that if you take a set of linear equations from which matrices follow, most of the linear equations are related to each other. So that means they are not really independent. So of course, like Sudoku, you should have some constraint, otherwise how do you solve it? Then she went through this algorithm which this MIT people have used by Prakash and his collaborator from Cornell, and she showed that if you take into account measurement through which information will be extracted, there is no advantage. So there is this recommendation problem that classical computers can solve the recommended problem as fast as a quantum computer. This is the first time it showed that measurement is highly non-trivial. How do you, the processing may go on faster, but when you want to read out the answer, you have to take into account that in measurement, so-called Goleva bound is there. One measurement will give you one bit of information. So the quantum speed up when we talk, very tricky. So every time people claim, there are counterclaims. For example, Google's claim of superiority has counterclaims now. So the good thing is that the mathematics that is required is not very much. Understanding of measurement and a bit of matrices. So that is how, and I was checking that paper of Yuan is now published. She is doing her PhD, 3 or 4 more papers. And so again, measurement statistics led to verification problem, and recommendation problem was solved by seeing that through measurement you can extract only so much of information. So understanding of measurement is very crucial, and now most of the quantum computers only needs understanding of measurement and matrices. MATLAB is enough. Very good. Now, for example, where are we as Indians? For example, if you see, ISRO has earlier initiated this project on space-based quantum communication, basically communication. And now there are realities, a little older one. For example, PRL, if you see Physical Research Laboratory, where I was part, Professor R.P. Singh and his group, they have a QKD quantum key distribution, more than 300 meter, optical fiber, IIT Delhi with the DRDO. They have also long distance in Jhansi, near Jhansi and some other place. And Professor Sinha also has something. So quantum key distribution has been achieved to a reasonable distance. The initiative started from ISRO. For example, SAT is now probably developing that technology, and they have a program. Now, the second part of the program is that which through satellite-based system to communicate with Canadian Space Agency. So, because Madam is there, you can check out her website for latest developments. So, there is a good, technological platform initiated by ISRO, which is engaged in communication related areas. But as you see, we are far, far behind than China. That if you see every other day, there will be some news item from China that through this satellite they have communicated with Vienna, from Lhasa to Beijing. They have communicated through entangled photons. They have an optical fiber line running between Beijing and Shanghai. So in communication, they have done quite well. They have satellites up there through which they communicate regularly. So communication is there for them. Now we have a long way to go, but we are now experimental front. Things are moving up. Okay. So for example, if you want to do QKD, I mentioned to you what quantum key distribution. See, this quantum key is basically a set of numbers like 0, 1, 1, 0, which should be agreed upon between two parties. Typically, we call them Ali and Bob. So they should meet together and somehow generate a set of numbers through which they can communicate and reliably. How do they communicate? As you are probably more familiar than this, you convert your message into a set of numbers. This key, which is not known to anybody and agreed upon by both of you, you encrypt the message. And the other end, which is far away from this point, this code Bob uses the key to extract the message, decrypt the message. That is the simple idea. And if you really see, it is nothing but 0, 1, 1, 0, a set of numbers with a key. Now, what is the quantum advantage? Where does it come in? This was realized by, accidentally by Brassard and Bennett when they were in Bangalore. there was a conference in 1984, and they had apparently the conference was the electrical engineering department. There was a physics person giving a talk about this measurement aspect. They first time heard that quantum measurement changes the state. The state can change if you measure. That is the thing that got in their head. If it can change, we can use it to generate a key. So they sat down, according to their own language, over a glass of beer, they came up with this thing. And it has not more than only measurement. You take single photons. Two things happen. When you measure, the state will collapse. So, for example, if you take a photon, it has 2 degrees of freedom. You can call it 0 and 1. If you measure, depends on which basis you are using. If you are using 0 1 basis, then you will get answer as 0 and 1. Otherwise, state will change. Keep that in mind. If you have created a state in polarization at 0 and 1, if you measure only in 0 and 1 basis, you will get the same answer. Otherwise, the state is going to change. For example, if you measure its basis, so-called Hadamard basis, the state is going to change. So that is the essential idea, that these two meet, establish the way they are going to do the measurement. Alice generates single photons, sends it to Bob. Bob knows which measurement basis to use. If he measures and finds it, then they agree. If Alice, in between them, there is one Eve will measure, the state will change. Then after measurement, let's say a little bit classical communication has to be involved. If you read it out, nothing very difficult. They compare their things, and while comparing, they know if Eve is present. Whatever Eve has seen, that's a key. So only thing is measurement. Measurement thing basis. Whichever basis it has been used to create, if you use the same basis, state is not going to change. If you use any other basis, state is going to change. State is going to change to that state in which you are using. So keep that in mind. Only measurement. And this is actually the technology now called BB84. You can see many companies are selling QKD using BB84. This is the simplest one, 1984. Came out from 2 persons who are basically computer science and electrical engineer. Bassard was from electrical engineering department of University of Montreal, where I hardly stopped. Nobody was taking him seriously. Bennett was the head of IBM. So together, you only hearing this thing, they came up with this thing. Now later on, for example, in 92 or 93, they came up with something called teleportation, which is a very miraculous application of entanglement. Now, if you work it out yourself, you will realize it's a very beautiful, simple application. And I made at least 3 times mistake on the blackboard when I was doing it. Any person who taught quantum mechanics too many times will make mistakes, because it does not really involve anything beyond use of matrices, vectors, and measurement. And that was a paper which only people of outside physics would have done it. I couldn't have done it because I didn't have this kind of application in mind. So what they did is that until then we were talking about EPR, Einstein-Podolsky-Rosen paradox. Bell pointed out in 1960s that if you measure and if you find these values between 2√2 and minus 2√2, if it is above 2, then it's quantum, and there is no hidden variable theory. If it is below that, then it's classical. Those experiments are done in the 80s, but we are still trying to settle the paradox and implication of that paradox. Local hidden variable theory being ruled out, loophole quantum correlations are non-local, they exist, quantum theory is complete. These people showed how to use entanglement. They used entangled particles like Alice and Bob to send an unknown information. State doesn't go. Some information gets recreated far away. And when it is recreated, it's exact, no mistake. Now, you can sort of ask somebody or work it out yourself. Take, for example, a Bell state, which like up, down, minus, down, up, or up, plus, down, down by √2, which we are all familiar. Take an unknown state psi, which is alpha 0 plus beta 1. You can actually work it out. It involves entanglement, measurement, entanglement monogamy, classical information. Information cannot go faster than light. All those things are involved. It's a highly, highly non-trivial example of many principles of physics coming together. And when I think about it, I could only see that people from engineering background would have thought about this kind of thing. And this has been experimentally realized across the Danube, now across satellite, and optical fibers across huge distances. So quantum teleportation is a key technology which has come out. You can send unknown information. Alice does not know what the information. Bob gets it exactly. He does not know what the information. Yet information has gone exactly. No mistake. remarkable application of quantum principles. Okay. Now, what people are doing. People are actually tempting their governments that will run things for you. You give us some money to do research. Sydney cluster has started, I think, last year. There are 5 universities that come together, and they are running through this quantum technology transport, Sydney transport system, so far quite reliably. Government has given them money. So there are computer science people, optics people, silicon optics people, designing chips. All those things are going on. But so far I haven't heard about any accidents. So it looks like transport network is working. And there are other places also where these things are going on. For example, quantum key distribution has been employed in many platforms. First time it, to the best of my knowledge, was this FIFA final in South Africa, where to avoid betting it was used. Now, every banking system, every defense people, everywhere you go, even in India or anywhere, QKD is being used for short distance communication, because that is a platform where you have reliably, you can send messages, encrypt messages, decrypt messages without third party doing it. Okay, so QKD technology is out there in the market, is being used. Teleportation is also there, not very extensively used, because it costs money in terms of entanglement. Entanglement you have to create, so you can think about quantifying entanglement. People have talked about 1 bit of entanglement, so hopefully in future, probably in future, entanglement will be sold. How much entanglement you are consuming in the process is a resource. But main point is this, that single particle measurement is something which you know how it will work. Entanglement is something we understand only up to 2 particles. Nobody knows the exact structure of entanglement, correlation, complete satisfaction up to after 3 qubit. 3 qubit also there are problems which we still don't understand. So you can imagine the whole field is open, and understanding of it is essentially mathematics, computer science, matrix algebra, linear vector space, nothing beyond that. Okay. So now, for example, where our neighbors are moving quite fast, and for example, Singapore CQT, there is a Center for Quantum Technology, which started early on, quite some time back. There are lots of good quality research that comes out of that, both fundamental level and technology level. Now they are building microsatellites. In NTU, for example, they are also doing quite well. They are concentrating on chip things. What are these chips? They are again silicon-based, quantum dot communicating through photons. So that is the kind of thing people are taking over. And many places. For example, there are companies now. I mentioned about CQT, National University of Singapore. So that microsatellite center, designing center, is apparently associated with them. There are other companies like, for example, you see Quantum C-Tech in Shanghai Exchange is listed. Now there are many, and IBM, Microsoft, Google, everybody else has some kind of a quantum object which are available, like the quantum generator, quantum key distribution platforms, and various things, quantum satellite. Okay. Now, for example, this all over the world, people are people started with NMR, nuclear magnetic resonance, as the only form of quantum computer. For example, in India, Professor Anil Kumar, IISc, was the leader. A lot of good works came out. For example, factorization of 21 is equal to 7 times 3, which is source algorithm, Peter source algorithm was shown there also. High quality information you can hide, cannot hide, no hiding theorem, Arun Pati, and has a very beautiful work with Professor Anil Kumar. And so many good results came out. A lot of people got trained. For example, Kavita Dorai in IIScr, Mohali, Mahesh, they are pioneers in quantum computation in Pune. Our Angit Bhattacharya here, many people got trained from there. Real experimental quantum computation. But NMR, you cannot go beyond 8 or 9 qubits because huge system, lot of noise. So now people are gotten into other things. In very near future, again the silicon-based quantum processors are probably ones people will be betting on. I heard many talks from people coming up with many kind of platforms, superconducting qubit, and then ion qubit. But the people who talk to really old timers, they say finally it is the silicon-based one at the heart with high performance computing at the exterior, and interfacing is probably going to the future. And because you have to do something called error-free quantum computing. Now, these quantum computers are highly error-prone. Everywhere there are mistakes. So somehow you have to do some kind of error correction, and which you probably can do interface with some classical and can do better. So that is the current belief now. For example, you see Finland, there is this Alto Alto, and there is a kind of private company. There was a 5-qubit quantum computer they were showing to CDAC that they want to sell them, which they have integrated with the European Union high-performance computing systems. So those are the kind of things people are talking. CDAC is probably getting into somewhere. They will buy a small quantum computer, integrate with one of the IPC, HPC quantum computer to build up the interfacing system effectively. So now, many of these things you can actually read in the mechanical quanta. It comes up with lots of recent developments. Now, what is a quantum computer? It pretty much looks like there are two platforms. One of the platforms, like IBM one, pretty much looks like a classical computer. If you go to IBM, log in, this 5-qubit up to 15-qubit, you will get access. And you will see these are lines. You can draw, drag a qubit. You can make it 0, 1. You can drag some gates. There are only 2 of them, Hadamard and controller. You can create entangled states, and you can play around. You can, for example, check creation of entangled states. You can do measurement, and one measurement will lead to collapse of the state. You can create the state in 0, 1, 1, do plus minus measurement, see what happens, and you can do QKD, quantum key distribution. You can do many more things. For example, early on we played around, we designed a quantum check, and it was quite nice. Money, there was problem because many rounds of circulation will be there, but quantum check was quite reliable to the extent that those early days, for example, Physics World called us up, took our interview, published it, quantum check. And so people are now coming up with these things. For example, you can think why quantum money is facing problem, not quantum check. Quantum networks you can build, many more small things you can do. For example, I saw IIT Hyderabad, Dr. Radhakrishnan, they used a IBM-based quantum computer to very accurately estimate the energy of, I think, hydrogen fluoride, lithium. We are also doing the same thing here. So small molecules you can actually measure, so build their states, and quite accurately, very reliable. And I just saw ECG Crest. They have this query. So Bhanudas is the head. I saw a paper where they were checking the efficacy of D waves, and IBM, they claimed D wave is giving you an answer much better than IBM. So those things people are now getting into it. So there are 2 platforms. I'll describe to you more. The principles is superposition, which is called quantum parallel processing, and entanglement. Entanglement is non-separability. These are the 2 key things which are being used. Other kind of resources are available. For example, quantum discord, many other things, and you have Alok as the local expert there. We can tell you about various kind of things. He's into this quantum foundation, quantum principles from quite early on, as remarkable contributions those areas also. Okay, so now, for example, you see what are the things which are unique, both particle nature and wave nature. Why did it come? Because I told you in 70s, they were talked about heating, and they knew heating is happening because non-reversibility. And then half kT is equal to 1 C-bit loss they established. But then Feynman came from a different angle. It was 1982 when we were doing our PhD. We were hearing this kind of stories that Dick Feynman has gone nuts. He was telling he wanted to solve quantum chromodynamics problem, confinement. He could not solve it. So he said that is where we should use quantum computer, namely solve big quantum problems. If you check, 1982 is the paper time where he wrote a paper on confinement, and he solved it in flat space, 2 space 1 time. Like, for example, in graphene, would not do anything more in 3 plus 1. So he came up with this idea. Why not have a quantum computer to solve big problems? He, of course, has other things, but so that paper, the basic design paper he wrote, paper was not being accepted anywhere. People thought he has gone nuts. So finally, this early journal, IJTP, International Theory, is where he published. Then it was David Doyce, 1985, who got this year's Foundation Prize. For example, you can check that Peter Shor, David Doyce, and these 2, Gannett and Brassard, they got Foundation Prize. That was for algorithm development. So both the Nobel Prize and Foundation Prize, both have come to quantum areas this year. So he showed a quantum equivalent of Turing machine, that you can actually design a quantum Turing machine. By mistake, I'm tuning, it is Turing machine, and a very shy person, and showed that 2 matrices are enough, Hadamard and control knot. I'll show you precisely that. And all the time people are using this particle and wave nature. Who came up with this particle and wave? It was our gentleman who is next to Feynman, this wave particle duality idea. That is what is being used. Then Peter Shor comes in. He shows that you can actually do much more. You can use a quantum computer to solve some complex problems. So computer science people have classified their problems. Something which can do in polynomial time, which is tractable. If it is exponential time, pretty bad. Then he showed this factorization can be done prime factor in polynomial time if you use a quantum circuit, and it is universal. That was a quite big breakthrough in 1994. Then comes Grover. He was engaged in some simple search algorithms. He points out that a quantum computer can do things much faster. If you read his paper, pretty readable paper, and in fact, what it shows that search algorithm you can implement through unitary matrix, which can be broken up into 2 by 2 matrices. And somehow, if you do 2 by 2 at a given time, you can do it much faster. Instead of n square steps, if you implement directly, you can actually do it much faster. There is something to learn. If you see fast Fourier transform, it works in the same way. Fast Fourier transform exactly does Fourier transform using two kind of things at a given time. So, how much time I have? Do I have 10 more minutes?
Yeah, 15 minutes.
Yeah. Okay. So now, unfortunate thing is that okay, so we have also our science day. So now, but if you see any algorithm which really has contributed significantly or people are developing, at the heart you will see Grover search. So it was quite unfortunate to see that he did not get recognition with Peter Shor and David Doyce and Bennett and Brassard this time. But heart of many of the quantum algorithms is this quantum search algorithm, that of Grover search, and it actually uses very simple ideas like reflection and looks for an unknown, looks for a state in a bunch of states together, and very quickly amplifies the state you are looking for, quote unquote, removes and kills the other states. Eventually, you zoom onto the state you are looking for. Very beautiful, simple mathematics, makes up the n by n matrix, the 2 by 2 ones, and accomplishes it in a polynomial time. Very instructive to read. Now, what are these 0 and 1? They are the states who are from the physics, for example, you realize they're simple matrices or vectors. For example, on the plane, you have x and y. Unit vector I and j can be thought of as 0 and 1. Except here in quantum systems, we realize them as matrices. As you know, Heisenberg, for example, came up with this matrix mechanics because he realized matrices do not commute and quantum mechanical things do not commute. So, of course, the web description came from Schrodinger, but right now we are using this very preliminary 0, which is a column vector 1, 0. 1 is a column vector 0, 1, 1. We call them qubit. Any two-level system would be a qubit. For example, electron in the ground state is 0, excitation is 1. So that is what, for example, in quantum dot, people realize. But any two-level system, if you think, it can be light, for example, photon polarization, 2 of them can be thought as qubit. So that's all. Now, what are the physical realization of qubits? Superconducting qubit, IBM, and many other platforms. Quantum dots now are becoming fashionable. Apparently, Samsung has put some quantum dots in some of their gadgets now. Trapped ion qubits, 20 qubit is there in the market. You can buy, very reliable. Photonic qubits, as you saw, Chinese are the leaders. You can check out this thing. They communicate through optical fibers, through free space communication. And we also are doing it through ISRO. Now, presently, this defect, for example, you got diamond, the color of the diamond, or for that matter, any jewel, comes because of defects. That was well known. Raman has studied extensively this kind of thing. If you go to RRI, definitely go through the collection of gems by Raman. Fascinating place, things to see. And the color of the so-called color centers are defects. Nitrogen, there is a defect in diamond, and yellow color comes from there. Apparently, that is a very pure source of single photons. And now everybody and his brother is talking about that. For example, technology has come out. There is a patent from IIT Bombay. Our Kasturi Saha for sensing purpose, sensing of very small magnetic field. So you can check, for example, IISER Pune, Mohesh has done some work. All over the world, people are using nitrogen defect in diamond for quantum computation as basic unit. Okay, so, and that one reason is that it is room temperature. The topological qubit, as you know, topology, for example, is something which is very stable. South Indian Boda and North Indian Boda are topologically inequivalent. If South Indian border is a torus, like a ring ball, North Indian border is a football, you cannot deform one to the other because topologically they belong to two different genus. Similar kind of ideas people have used in qubit. And why? Because it will be to resist errors. Try to change it, it will not change. So Microsoft, for example, has put a lot of money onto it. So they're using the so-called Biorona particles for this purpose, but unfortunately there was a setback. The papers were withdrawn last year from Denmark, but people have not given up. People are trying to come up with other platforms to realize topological qubits. Main point is that it will be error-free. NMR, as I showed you, early on, all over the world, many non-trivial results have come, and now slowly people are coming out of it because for reproducibility and bigger thing not being possible. Okay, so unknown state is alpha 0 plus beta 1 vector addition. Only thing that quantum is that if you take this unknown state psi, if you measure, first you have to tell which basis you are using. Suppose if I am using 0 and 1, I'll get either 0 or 1. Now, which one 0 or 1? Nobody has any idea. A given measurement will give you either 0 or 1. Alpha beta, if they're 1 by root 2, 1 by root 2, if you do thousands of measurements, half of the time you will get 0, other half you will be 1. Why it is so? The first thing is called collapsal wave function. When you measure, it will collapse to the basis. For example, if you take a vector A, it has components I times AX plus J times AY. If you do a projection, the vector is not going to collapse. You will know AX and AY. First, you measure AX by collapse by looking at the projection along the X direction, like we do polarizer analyzer. The state is going to remain same. State is not going to collapse. But quantum's problem is this: the unknown state will collapse to 0 or 1. That is Copenhagen interpretation of quantum mechanics. And please think about it: the difference between this and a two-dimensional vector. A two-dimensional vector is not going to change because of measurement. Here, the state is going to change. That is where this idea of QKD came, that Eve is going to look at the state will change. The see the Toronto, which basis has been used to prepare it. This is also being used for taking unknown state, teleport unknown state from Alice to Bob with complete fidelity. Unknown state. So it's and unknown state cannot be xeroxed, cannot be created. As I told you, no cloning theorem. All of this key is psi, unknown state. So now why 50%, 50%? If alpha beta is equal to 1 by root 2, that is due to statistical interpretation of quantum mechanics by Born, Jordan, and many others. So quantum mechanics emerges statistically. You have to take large number of measurements. Now, what are the technologies? First is QKD, I told you, 1984, BB84 has come out of it. Second thing is random number generator. You can check now, NIST, USA, NIST, University of Colorado. They are actually generating random numbers in this process and broadcasting it. So in your MATLAB, when you do Monte Carlo, if you need random numbers, you can actually use that. It will give you much convergent answer. So those are the two technologies you can actually check that QKD and quantum random number generator are mature technology available in the market. Government of India has a protocol now. If you have a company trying to sell QKD, what kind of tests have to be done, and what are the guidelines for it? Those things are now documented. You can go to their native website. It is adopted now. So these are technologies which are becoming mature, and they're only because of measurement, nothing more. Measurement principle of quantum mechanics. And if you ask, we still don't understand why the state collapses, what it collapses. Okay, superposition, add them up. If you take, for example, ammonia is always going from one pyramid to the other pyramid. It is oscillating. That's a case of example. Double well potential in quantum mechanics. State could be here or there. So superposition is intrinsic to quantum mechanics, and is also non-local. That double well, either here or there. If you measure, if it is here, then it is not there in the other well. So if you don't find it, it's there in the other well. The state will collapse when you do the measurement. And this kind of correlation is non-local, because between two wells, they could be far off. Okay, so now entanglement, this word came due to Schrodinger, non-separability. The paradox started because of Einstein and Podolsky and Rosen, 1935, beautiful paper. The state they used is a bit difficult state, involving continuous variable states, which later on Bohm showed you can do it using spins, 2 by 2 matrices. That was used by Bell. And Bell actually took a statistics, bivariate statistics analysis by Boole from 1887, converted into a quantum analog, exactly same thing, except instead of statistical average there, it was average using a singlet state. And there it was 2 to minus 2, it is 2 root 2 minus 2. Many of you are curious to work it out because it uses polymatrices whose answers should be plus or minus. Instead of Bull, who was a statistician, I talked about coin tossing. The same thing, 4 terms, 3 positive, 1 negative. Then it was average by coin tossing, 2 parties. Here it is between singlet and 2 root to minus 2. So, and that was the experiment which was done in 80s. So, superposition and entanglement word, and the meaning of it, it was really Schrödinger who perceived what is the physical meaning of it. And now it has become a key resource for us, and it creates a real difference between classical and quantum world. But amazingly, when you do something with it, the entanglement is lost. Teleportation, if you successfully do it, 1 EBIT of entanglement is lost. You have to really pay for it. Otherwise, you cannot teleport. Now, what kind of experiments these people did, whether were right, they did something called coincidence measurement. So, 1 photon is coming out. Suppose the state is XX, YY. If you find X as, and they are basically 1 and minus 1. If you find 1 here, you must find 1 there. This coincidence kind of detection was used. Very sensitive experiments. I am, 80s, for example, if you check Professor Rupamundari Bose, who, whose 65th birthday was celebrated yesterday on Saturday, has done, you can check it out, has done quite a bit of remarkable experiments with Professor Mandel. She was my senior. She unfortunately had not got much credit. You can check. Many defining experiments, non-locality, has been done from Rochester, thanks to her, she being the first author. So, I mean, unfortunately, I really feel bad that she has not got much credit for what she has done with Mandel in Rochester. Okay, so these are the platforms available. You choose your thing. Money is there. Government is giving money also. And DWeb is reliable now. People believe it's a quantum computer. And as I told you, because Bharanda showed, in certain cases, DWeb gives you more advantage. And all the others are available. Okay, how does the quantum computer look like? This one of IBM looks like it has a electronic circuit, and whole thing is in liquid helium because you have to pull it up, and you can access it through electronics. They talk to each other by photons, so not very easy kind of thing. But they are all there. They look fairly like the old time when von Neumann designed the machine, which was a huge one. And I'm pretty sure things will become smaller and smaller as you go along. Nitrogen defecting diamond is at room temperature. New technology will come, but essentially, pretty much like a human brain, it works. And it uses only 2 matrices. Quantum logic gates, it's called Hadamard and control knot. Okay, so how does the Hadamard look like? What does it do? It creates superposition because you need superposition. So it's a 2 by 2 matrix. As you know, Hadamard knew it much before than us. Polymatrices were there, for example, in optics. So same kind of mathematics we use, nothing more than that. If you talk to Grover, Grover will tell you he doesn't know anything except this polymatrices, 2 by 2 matrices, and something called measurement, which he understood from his friend. So it creates superposition. Now, control knot, what it does, it negates. There are 2 parties. So it involves 2 parties, Alice and Bob. You can check the truth table. If Bob is 1, Alice will change. So you see the second one, input Bob 1, Alice 0, Alice is to the left. Output will be 1, 1. Similarly, if it is input 1, 1, output will be 1, 0. And it was David Deutsch who pointed out, Hadamard and control knot are enough. Everything you can do using it. So you can create entanglement. Okay. Now, as I told you, this Toffoli, for example, in 70s pointed out that you can do computation without loss by a 3 qubit, and people in fact have used it. Once quantum thing was understood, it was found out Toffoli is nothing but control net. The truth table is here. 2 parties, if they're 1, third party is going to change. You see, the white fellow 1, 1, 0 becomes 1, 1, 1, and is actually unitary. That was the reason why there was no loss. Toffoli gates are now being used also. All right. So the universal quantum computer you can design, and you don't need anything else. Toffoli is a pleasure for you, but if you don't want to use it, don't use it. You can use control knot or Hadamard, enough for you. Now, what are the types of computer? Primarily 2 of them. DWeb is an annealer. What is annealer? For example, you have a Ising spin kind of system, completely Ising model. It has been shown that you can use Ising model processes to solve a real problem, like factorization. So this is the kind of thing they use. They will put their problem into the Hamiltonian parameters, let this system evolve, and you will find out that once you read, your answer will come. Achha, if you ask me how a quantum computer, which people ask, solves the problem, I can only tell you that nature is very powerful. If you put 92 protons, 92 electrons, and some more neutrons, it will solve, for example, uranium problem for you, all the energy levels. So that is the kind of thing what it does. So many things people have shown using DOFs. You can go to the website. IBM is analog, namely gate-based. Electronic structure is pretty much looks like our good old ones. There are many platforms now who are using analog. You gate-based. You know every step you have control what you want to do. But there, the development of the algorithm is the challenge. Okay. So Bell state, as I told, you should play around with it if you have. For example, if PRL guy was there, I did not understand Bell state. I started asking many questions. What is so special about this state? He taught me something called entanglement, for which I found out that if there are two vectors, entanglement can be understood as an area between them. Entanglement geometrically can be understood as an area between them. Then while quantifying it with a BSc student who is now in Toronto, Vinit Bhaskara, was from Hyderabad. So we have that paper. We found out that a very beautiful cross product can explain entanglement, which is called Weiss product. We needed an identity or Lagrange identity, like a triangle inequality, Schwarz inequality. But it was told to us by one MIT mathematician that this inequality was due to Brahmagupta. So using good old Lagrange Brahmagupta identity, using vectors and their areas, you can actually quantify entanglement. So if you are curious, you can check out Vinit Bhaskara, myself, and later on other works are there, that actually entanglement is a property of vectors. Area is one of the things which can be used to quantify. But I can also tell you that having a deeper understanding of entanglement beyond two particles is still a challenge. And it's also a challenge for mixed states. And what kind of resource it is. So a lot of open questions are there, but it makes you familiar that our vector space are vector space. So it has length, it has area, orthogonality. Those are the kind of concepts that goes into understanding of entanglement. But measurement is another business. Now, for example, you see Bell state, you can actually create this way. And I'm at control. They are maximally entangled. You want a bit of entanglement they have, you can actually create them. These things, you can check that was the property by playing around with IBM. Now, you can actually, this Greenberger, Horn, and Zeilinger state, was the state which you have one more. So 0, 0, 0 plus 1, 1 by 2. And believe it or not, even now also 3-qubit states, there are many aspects which are not understood clearly. Okay. So this was, but it showed something better than Bell state, namely, it could show this Bell inequality for all angles between the spin. Bell inequality, if you see, if the spins are parallel or have a 180-degree angle between them, there is no result from there. This was because of which this GSS state became very popular. So now you can check this state is still a lot of things are there which you don't understand. Okay, quantum teleportation I mentioned to you, just to appreciate it. Unknown information goes from one side to the other, state gets created, state physical doesn't. And if it's created, it has all the aspects to it. How do you implement it? Circuit is there, check it out in IBM. Now, if you have created a Bell state or a computer, quantum computer, you can check if the quantum computer is intact or not. You extract information from it and measure outside, but the state remains intact. So you can see here, entanglement doesn't get destroyed. So these are the kind of ways you can actually check if your quantum computer is working or not. This was the thing which I started in PRL. My life started from here. Fortunately, an MR experiment was done by Anil Kumar, where we are also part of it. So you can come up with something where you can extract information. It taught us that only hollow bound is there. You can extract only one classical bit of information at a given time. This is long because here we could not extract anything more. Okay, so no cloning I mentioned, you can unknown fellow, you cannot create. You cannot hide information. You cannot remove information. There are things which you cannot do through data transformation, you cannot do at all. This is the very famous paper of UPR. And if you go through it, very carefully written paper, now people believe that quantum theory is non-local but complete. But these have led to so much of debate now, so much of technology also. Now Bell's paper is there, you can check that he has used really Boole's identity of classical statistics replaced with operators to rule out hidden variable, and or if hidden variable there, what should the answer? And real interpretation of quantum mechanics is possible through that. Very simple calculation. Okay, this is the papers of going beyond Bell's theorem, and what was the need for it? Because there are certain cases Bell's theorem was not giving you any answer. So 0 degree between two vector spins or 100 degree. All right. So now people are, for example, using this CPR thing to do many things, and really using as a resource. Apart from entanglement, you can use other kind of resources. So quantifying different kind of non-locality quantum correlation is a big game. Even coherence also. Okay, people have, for example, this paper shows entangling physical qubits which is like quantum system with outside insects and tardigrade or something. Basically, microscopic and macroscopic world, how they communicate with each other. Where classical thing comes from the quantum world is a big area, completely time. So now I'm open for questions.
So thank you very much, sir. It was very interesting and stimulating talk, as you always used to do. And now I request Alok to moderate the session. So Alok, please take over this. Do you have any questions? Mike. Yes. Yeah. Go ahead. So, and you the talk. Sir, can you hear?
Okay, maybe you can just speak a bit loudly. Yeah. Yeah.
Thank you for the talk. I would just like to ask, in the recent years, there has been this quantum hype about quantum computers being developed and maybe overtaking classical computers in the next 10 years, 20 years or something. But there are other people also saying that we are overestimating the hype about quantum computers and that the physical technology right now might not develop as far as the algorithms and the theoretical side is developing. Like recently, I'm not sure how recent, but Shor's algorithm was run on an IBM computer and it was able to factorize numbers like 15, but it was breaking down on numbers like 35. It was unable to factor them into primes. So, what is your opinion on the future of quantum computing and how much time do you think it might take for actually quantum computers to take over? Or is it something that will be very niche and very limited to a particular set of computers?
You see, I mean, you have a point there. You see, it is actually true. Whenever they say there is some quantum advantage, people eventually find out to fault with that, including that Google's claim of, quantum advantage. So as you mentioned, for example, this source thing is the only thing, and it is not very fast. So people have shown experimentally that there is this fractional revival based algorithm called Gauss sum. That after it gives you the fastest one. Source is not very fast. So therefore, but source thing uses really quantum. Grover's thing uses only superposition. So you don't need really many wave phenomena will do it. So for example, now if you ask for technology, are they reliable or not? In ion 20 qubit, that ion platform apparently is quite reliable. Similarly, D waves. So and I was there in CDAC recently. This IBM people announced they have a 334-bit quantum processor with almost 99.99% error free. Error is the main problem. So they're apparently betting money on it, and to me it appears that really serious people are in it, and the advantage or not, that needs more careful consideration. For example, that 2009 linear equation solving, it was shown that the quantum computer can do faster than this thing. These Chinese people last year, they showed that they have some quantum advantage. It was a huge experiment, 500 lasers. So, essentially, you have to have your own clever way of doing it. Suppose if you want to do a quantum computation, question is why? So 0 and 1, see, classical advantage is 0 and 1, no error. Quantum there will be error. So what problem you see, to me only, source algorithm is one which is really non-trivially needing entanglement because it does quantum Fourier transform, then measurement. So which, has this entanglement stress as building block. But, it is not very fast. So, I really cannot say, but quantum computing is a reality. And what I heard from industry people, at least this ion and this IBM fellows, they have real machines which are coming up. Okay, and the US people are taking them seriously. They also have sold machines to NASA and to US defense, other places, and also outside, which are quite big, quite reliable. Advantage or not depends on you, and serious people believe there will be advantages, but it's up to you. For example, for confinement problem, Feynman started. If somebody can show this SYK model, for example, those are the, if you can really come up with something where a classical computer cannot do, and interfacing classical and quantum is a big challenge, even theoretical. You can ask Alok; he will explain to you more how to things go from quantum to classical. Nobody knows. So I am bivalent. But I am optimistic that quantum computer will come. How to use it is up to us.
Thank you, sir.
Hello, sir. Can you hear me?
Yeah, I can hear you.
Thank you very much, sir, for very inspiring talk, very interesting talk. I have some very basic question. How much a typical quantum computer costs? And second question is, what is the most advanced problem that can be solved easily by a quantum computer today?
How much does the quantum computer cost? See, I mean, for example, the things which is quantum technology, which is out there in the market, is a random number generator, UKD generator, right? Those are things which are out there in the market. I think they're around less than $10,000 or something. There are 3-4 companies who are selling it. See, I only keep track of this thing. I am not going to buy a quantum computer. But it's 20 qubit ion quantum computer, people claim is quite robust. And the very neat thing is, there's a company which is selling it. Okay. Now, how expensive they are, I don't remember. You can check out these things. But when you are asking me, what kind of problem you can solve, I can tell you very clearly that, some of these ground states of, this European Union has a huge project. They use this tensor product state, tensor flow. Some of the many body ground states, they have been able to estimate it very accurately. Because this is what I saw. I was in the Austrian Science Foundation, Alok knows. Many of Alok's ideas have been tested there also experimentally. So many of the ground states they have found quite accurately. Now, any other thing what you ask, for example, I don't know. I mean, nothing very significant like that advantage of random variable kind of thing what Google was claiming. People have claimed it is false. So I don't know really. But many body ground states, I know, apparently quantum is doing much better than standard packages.
Thank you.
So I can ask. I can ask a question. Maybe it is a question for everyone here. So where do you stand compared to the world research of quantum? And maybe the next question will be when we will have our own Make in India quantum computers?
See where do we stand? I mean, I can have a long lecture from Alok himself once he's free. See, if you ask, theoretically, we do have good contribution, we do have good understanding. And I would give a lot of credit to Calcutta, where, Guru Prasad Kaur, Dipankar Home, and many others trained people in the quantum information theory. Quantum information theory is quite non-trivial. It's not easy. And we have a very good understanding, thanks to many of the schools and things like that, if you check out. And NMR quantum computer, thanks to Professor Anil Kumar, we have a good understanding about experiment. Practical quantum computer, we are honestly speaking, we are pretty much, way below in the world. For example, government has told us to come up with a 4-qubit, quantum processor, which I don't think, many people except TIFR, Vijay Raghavan, who are just for 20-qubit based thing. Communication, we are doing similar kind of things. Nowhere that sophisticated, but at least, like RPC in PRL, Urvashi in RRI, and this IIT Kharagpur, Joy and Kanseri, optical fiber based. We are now, for example, in a way where it has come up to a level where you can really compare yourself with some labs in the world, but nowhere, in the front ranking. And qubit, for example, quantum chip, nowhere. Very honest opinion.
So that will take time. That is, to make our own quantum computer.
I have no idea. Vijay Raghavan is building something. You can check his website, 4-qubit or 3-qubit quantum processor. Quantum computer, I absolutely no idea.
And also, you say there's a guy, there's a girl that is tested this quantum verified quantum computer. So it is a very interesting question. That is, I build a computer, whether it is performing better than any existing classical computer or not. That's an important question. Otherwise, why do you spend such amount of money and then effort to make a quantum computer? But interesting is that this kind of research in India, it will actually not doing. So what is the problem? Because this is theoretical research that we can also do, right?
Yeah, really. Even algorithms. See, for example, this time this IBM people were complaining, that Indians, why you see Indians are not doing algorithms? Because we have a lot of trained people, as you know very well. That there are a lot of people who understand. They all, go out and get jobs. You see now any lab in the world filled with Indians. For example, Austria, Australia, Sydney quantum cluster, 12 or 13 kids from here went there. All the labs are full with Indians. But right now in India itself, I don't know. I mean, I leave it as a challenge to the younger people. They should really get into algorithm, games, design quantum games. There is a IBM quantum computer available. Play around, design quantum games. I know that. So it's basically a challenge for us. And also, for example, Israel is such a small country. Israel is doing so well. All this nice this thing. That is what actually many people are wondering. That why there are so few algorithms from India. Hardly 4 or 5 only.
So there are many young students. So what message you want to give to them that is around to do in quantum research?
See, I tell you very honestly, just sit with one faculty, learn about measurement and collapse of state. Play around with IBM, and now access you will get to many of these things, and start playing around. And the moment you go beyond 2 particle, 3 particle, or 2 particle mixed state, there are enough number of open questions are there. You can really do fundamental contribution sitting right now, for example, in Mohan here. Just play around. Beyond 2 bit open area, completely open.
Okay, thank you, sir.
Thank you. Yeah. Thank you again. Thank you for inviting me.
So thank you again, sir. So just to the students, like if you ask me to show a faculty or a researcher who is an open book, I would first say the present Panigra is actually an open book. You can have a discussion for a day or a week, continuous discussion. I just wanted to remind one more thing actually, sir. I just want to share with the students. Of course, you have no reason to remember this story. And I met him in one of the conferences. This is Sri Pune, sir. So we met in Senior Sri Pune way back 2012 or 13. I had a very puzzling question. This was on bistability, optical bistability, something like that. We had a discussion. And in the next meeting, it was an Isar Mohani, if my memory is right. You still remember that we engaged in a discussion on that particular problem. Okay. So anyway, so that dedicated researcher is Professor is. And I also wanted to say that you promised me that you will be coming on June 6th.
Yes, definitely.
That will be an opportunity for all of you to have a physical interaction. So we'll be planning something on June 6th. So we'll be having some interaction there. So thank you very much, sir. I'm going to pass it to our head of the department, Professor Prempa. He will be giving next few words. Good afternoon, sir.
Good afternoon.
And on behalf of our organizing committee and the Department of Physics, I sincerely thank you, sir, for accepting our invitation and giving an outstanding talk. And as you know that we are going to start a tech program in quantum and solid state devices from next academic year. So this talk is really very, very inspiring and very important for us. And thank you very much for accepting our invitation for a short notice. And I'm very happy to know that you are visiting us in June, that we will have some more detailed discussion, especially about our program, how to make it more and more successful. And really thank you very much for accepting and giving it up.
Thank you so much. Yeah. See you in June.
Thank you, sir.
Thank you.